Okay, so hello, I just started recording. Um, I started recording like 2 minutes late, but basically all we're doing is reviewing molecular orbital theory. All right, so let me restate my last question that I asked. So, how many electrons are in the HOMO in the excited state? One, I totally agree. And we know that there were two in the ground state, and then one of them moved up to the LUMO in the excited state. Cool. Perfect. So let's say we have the allylic radical. How many pi electrons do we have? How many total pi electrons do we have? 3. I agree. Okay, so how many non-bonding orbitals do we have? 1. Awesome. So now how many non-bonding electrons do we have? Also 1. Perfect. Okay. And what is the name of the HOMO orbital? So like pi 1, 2, 3. Pi 2. Yes. Perfect. Awesome, awesome, awesome. Okay. So let's say we have the cation. What is the hybridization of the cation? And so what I mean by that, sp, sp2, or sp3? sp2, cool. And how many electrons are in that p orbital? Ooh, this is a tricky one. It's 0. Yes, and so it's 0 because it's a plus charge. If it was a negative charge, there would be 2 electrons there. Awesome. And so, okay. Yes, I can repeat. So basically what I said is how many electrons are in the p orbital of this cation. And so if I'm only talking about the carbocation, we're talking about only this orbital. And since it's a plus charge, it means there's 0 electrons. If we were looking at the anion, which is a negative charge, we would have 2 electrons here. Can you guys see my blue thingy? I think you can now, but I don't think you could before. Okay, so my last question for this one is what is the most favorable energy transfer? AKA, when I excite it, where is the electron going to move from? From where to where? From HOMO to LUMO, yes. So I'm going to write LUMO, but I want you guys to tell me like from pi 1 to pi 2, pi 2 to pi 3, pi 3 to pi 4, like that. Please. Yes, I can definitely repeat it. So you guys were absolutely right. It is HOMO to LUMO, but I want you guys to tell me more specifically. So give me the pi numbers, please. Pi 1 to pi 2, exactly, because there's only 2 electrons. So pi 1 is the HOMO. So we're going to move from pi 1 to pi 2. Cool. Perfect, perfect, perfect. So let's say we have the anion now. So how many number of antibonding electrons? So in the ground state, how many antibonding? 0, exactly, because there's only 4 electrons and that only fills up 2 energy levels. So the antibonding is 0. In the excited state, how many, do shorthand again. What's the number of electrons in pi 2?
1.
Yes, so we got a couple different answers. The answer is 1, and the reason is once you excite it, 1 electron moves from pi 2 to pi 3, so you have 1 left over in pi 2. And I'm trying to think of like one more question to ask. How many bonding orbitals do we have? Yeah, just 1. Okay, cool. So you guys are killing it. I have nothing left to teach you. Okay, someone asked what. So basically all I asked was how many bonding orbitals do we have? And we only have 1 because this is going to have 3 orbitals. The first one will be bonding, the second one will be non-bonding, the third one will be anti-bonding. And I can go up to what we did last time and actually show you how it looks. So remember, pi 1 is bonding, that means pi 3 has to be anti-bonding, and the one sandwiched in the middle has to be non-bonding. Does that make a little bit more sense now? Oh, okay, yeah. Yeah, that's why it's so important. Like when you see these kind of questions, I want you to immediately think, is it the cation, anion, radical, or diene? So you know exactly what you're working with. And then I want you to think, are they talking about orbitals or electrons? Because that's when it gets pretty confusing. All right, so I'm going to leave this here if anyone wants to take a picture or anything, or if you want to ask questions. And then in a moment, we're going to flip over to the chapter 14 handout. Excuse me, I thought I was going to sneeze. Any questions, comments, concerns, anything of the sort? Alrighty. All right, so I mentioned that we're going to move on to chapter 14, but I forgot that we have to review and finish up Diels-Alder. So we're going to finish that, and then we'll do everything else in the coming sessions, excuse me. So a quick review of what we did last time for Diels-Alder. All we really did is a quick intro. We talked about how in this mechanism, all the electrons are going to kind of go in a circle, and we make a 6-membered ring. Cool. We then talked about the 2 components for this reaction. So we have the diene, which is the nucleophile, and the dienophile, which is the electrophile. We know what a diene is already, but the dienophile can be any alkene or alkyne, so any double or triple bond. And we also talked about electron donating and electron withdrawing groups. So we know that the nucleophile wants more electrons, so it wants a donating group. And we know that the electrophile wants less electrons. It wants a positive charge, so it wants a withdrawing group. And then we're not going to go over all the withdrawing groups again because it was a lot, or all of the donating and withdrawing groups again, but I will show it to you. And if anyone has any questions, like specifically about them, we can definitely answer that. But if not, we can move on. So I will give a moment for any questions. Okay. Again, if you have questions at any point, please let me know. But we're going to move on. So I'm going to go ahead and number these for you all so we don't get confused when we go over them. And we're just going to go through and we're going to label diene or dienophile. And since we just reviewed kind of what those two terms mean, I'm going to point to something and you are going to tell me what you think it is. So this first one, what do we think? Diene or dienophile? Diene. Correctamundo. All right, so what about this thing? What do we think? Number 2. Número 2. Okay, so one person said diene, one person said dienophile. So let's think about it. There are 2 double bonds, so a lot of people get, can you guys see my laser pointer? There we go. All right. So we do have 2 double bonds, but this guy up here is not going to act like a diene double bond. It's actually going to be a, what kind of group? What do we think? What do we think? What do we think? Electron withdrawing group. So I'm just going to shorthand because I'm lazy. So this is going to be an electron withdrawing group. So that tells us that
Rose,
this
I have
is,
a question.
yeah, what's up?
How can we tell that one is a donating and one's a withdrawing group?
Okay, good question. So that kind of goes back up to here. So donating groups are going to be anything that has a negative charge or a lone pair or an R group. So all of these things are going to either by resonance or by electrophilic effects, or excuse me, electronic effects, they're going to donate electron density. Whereas withdrawing groups are anything that has a positive charge, anything that has a carbonyl, or anything that is a halogen. And so the reason those are withdrawing is because they're going to pull the charge away by either resonance or electronic effects. So for example, here we have a plus charge, and we saw that through resonance, the electrons go through these atoms, and through electronic effects, the electrons are pulled from this double bond into the plus charge. Whereas these donating groups, they have a lone pair, and so they can go ahead and through resonance donate their lone pair, which will help the double bond then give its electrons to attack.
Gotcha. Okay, I see. But then the other one that we just did had an O, so wouldn't that be a donating group?
That's a great point. And the O's get a little bit tricky. So, what I always tell people to keep in mind is the carbonyls, right? So, if the oxygen is directly attached, that's when it's donating. But as soon as you put this double bond here, that's when it becomes withdrawing. And someone asked me to zoom out. So, yes, I can do that. And so, carbonyls are going to always take the electron towards the oxygen. The lone pairs are going to give the electrons into the system. So that's kind of the differentiating factor. And someone asked a great question. So does that mean the dienophiles can be conjugated? So yes, they can be conjugated, but they have to, in order to be a diene, you have to be a conjugated diene that has both of the double bonds to a carbon. So carbon, 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 versus here, carbon, 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 oxygen. Blah. Yeah, that's how you. So on the exam, if you ask a question like this, be like, blah. Sorry. All right. So this next one, what are we thinking? You know what? First and foremost, before you even tell me diene or dienophile, um, what kind of groups are these? Are they donating or withdrawing? Yes, 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 yes. Everyone got it right. They are electron withdrawing groups. Perfect. And which component likes withdrawing groups? Is it our diene or dienophile? Dienophile, yes. Okay, and so again, I'm lazy. So diene is going to be D, dienophile is going to be DP. So I'm going to say DP. All right, super swag. For this one, we have another group, right? And we have an oxygen. So is this going to be a donating or a withdrawing group? And someone asked about the donating and withdrawing groups chart, like they want to take a screenshot. So after we do this one, I will go back and let you guys screenshot. Absolutely. So yes, I think this is an electron donating group because of those lone pairs. Absolutely. So do we think this is a diene or a dienophile? A diene, yes. Okay, perfect. So, ta-da, you may take your screenshots, write your notes, do whatever. And while I show you this, I just want to mention, so we know that dienes like donating groups and dienophiles like withdrawing groups, but it's not impossible for a diene to have a withdrawing group, right? So it can happen. So just because, like, if something looks like a diene and it has a withdrawing group and you're like, oh, maybe I'm just wrong, it can happen, but it's going to be much less effective. So if a diene has a withdrawing group, it's going to be really crappy. If a dienophile has a donating group, it's going to be really crappy. If it has a group that it wants, so the diene donating, dienophile withdrawing, it's going to work much faster and much more efficiently. And someone unmuted, so did you have a question?
Yeah, Rose, didn't you say that to be a diene, the double bonds have to be on the same like side? So I guess cis, or am I thinking something else?
No, no, you're absolutely right. So in order for it to work, it has to be an S-cis conformation. So that's actually a really good point because there's some examples we're going to cover. If they give it to you trans, you then have to think to yourself, can I convert it to cis or is it stuck? If it's stuck trans, you cannot do it. If you can rotate it to cis, then you can do the reaction. So that's the differentiation there. But I'm glad you brought that up because it's very important. Zoom, 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 zoom. Okay. And yes, I ask a question about that on the next page. All right, so for number 6, what do we think? This one's a ring. Yikes. Rings suck, right? Did we do 5? No, we didn't. Thank you. All right, so Since you brought it up, what do you think about 5? Diene. I would have to agree. All right, and so just for giggles, what kind of groups are these? Oh, didn't even have to ask. You guys already answered it. They are donating groups. And we know that because of these swaggy lone pairs. Yes. Okay. Coolio. So now we go to number 6. Now we have that ugly, disgusting ring. So is it going to be a Diene, a Dienophile, neither, both? What do we think? Diene. Yes, I agree. So it's going to be a Diene. And does it have any substituents, like donating or withdrawing group? No? Are you sure? Sorry, now I'm just being annoying. Um, okay, so actually, the spicy part of this is that this carbon group is a substituent. So this is going to be an electron donating group. And the reason it's a diene is because we have double bond, single bond, double bond, and all of these guys are carbons. If you're wondering, wait, how does this reaction work with a ring? We're going to talk about it on the next page. And someone asked, how do you know it's an electron donating group? So we know that R groups, so like carbon groups, are going to electronically, that's not the right word. They're going to just donate electronegativity, gosh, excuse me, through electronic effects. So they're going to very lightly donate electrons. So all R groups are going to be donating groups. And I can put that in parentheses. Yes, and so R groups. Okay, so lone pairs, this one does not have any lone pairs, but lone pairs we were talking about for the last one, the reason this one is donating is because it has a lone pair. So withdrawing because of the double bond, withdrawing because it's a halogen, donating because of the lone pair, donating because of the lone pair, donating because of the R group. So on to this one, we have 2 R groups again. So is it donating or withdrawing? Withdrawing. So we're going to say EWG. Oh, just kidding. You tricked me. You said it confidently. It's an electron donating group. I'm so sorry. So yes, it's a donating group because the R groups are always donating. But now it's exactly. So someone said, but it has a triple bond. That's the tricky part, right? Because a triple bond isn't a diene, so it has to be a what? A dienophile. Exactly. And so this is why I made that note of it's not impossible for the dienophile to have a donating group, but is it going to be a really good dienophile? No, not at all. It's going to be kind of gross, to be honest. Cool. So this next one, substituent, substituent. So these substituents are what kind of groups? Electron withdrawing, and why are they withdrawing? Because of the carbonyl, exactly. So the carbonyl, this double bond is withdrawing. And then is this a diene or a dienophile? So it is conjugated, but it's going to be a dienophile because remember, those double bonds in the diene all have to be to carbon, but here we have carbon, 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 oxygen. Ew. Carbon, 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 oxygen. Ew. So it doesn't work. So it has to be a dienophile. Okay, so close. We're almost at the end. Alrighty. So now it's tricky because we have one double bond and one triple bond. So let's call this A, let's call this B. Which one is going to react towards a Diels-Alder reaction? A or B? Or both or neither? What's the question? Okay, so I'll repeat the question. So between A and B, since there's two groups here that could react, which one will be the one to react in a Diels-Alder reaction? And we got a couple B's, but mostly A's, and I would have to agree. And so if you said A, why is it not B?
I just don't see any way that resonance can be moved around with B as it can with A to break it apart to give two separate products.
Okay, that's a good point. Um, the other part of it is, what did we just say about this oxygen? Remember when I went, ew, right? Right? This is a nitrogen. That's not a carbon. Ew, right? So this can't be a dienophile because it's a carbon and a nitrogen. Ew. So this whole thing has to be a substituent. And so what kind of substituent is this? Someone said
Electron withdrawing?
yes. So I would have to agree it is withdrawing. And someone actually had said, isn't nitrogen donating? Well, kind of. So nitrogen by itself is a donating group because it has a lone pair. However, we're not looking at nitrogen by itself. We're looking at this. But he was super tricky. He didn't put the C. He just like showed it to you as a dot, right? So that's why a lot of people get confused because they forget that CN looks like this. Ah, okay, like this. So always remember carbon is good, nitrogen, ew. Oxygen, ew. It's not going to work. And someone wants to take a picture. Yes, let me just finish up this question and then tell me what to take a picture of. All right, so we know that B is a substituent, and that means A is going to be what reacts. And so is this going to be a diene or a dienophile? Dienophile, I agree. Cool. All right, and so are we done with this one? Anything else? Any other substituents? The ring, yes, and the ring is an R group. So is that donating or is that withdrawing? Two people said withdrawing, but R groups are donating. So remember, always R groups are donating. Yeah, so basically any group connected here is going to be counted like as a substituent. So like this is technically not a substituent of the double bond, but it's connected to the compound. And so we're going to consider if it's donating or withdrawing. Yeah. Sorry if I know substituent technically is not that definition, so I'm sorry if I confused anyone, but that's how I was using it kind of. All right, so last one. Yay. Okay, so is this a diene or a dienophile? I don't know why, but when I said that, I imagined you guys being like, I don't know, you're the tutor, you tell me. But you guys all answered, so. Okay, so we got mostly diene, and I would have to agree. And I know someone's thinking in their head, but you just said oxygen is ill. I did. However, is the oxygen part of the double bond? No. So now it's not just ill, it's a substituent. And is that going to be donating or is it going to be withdrawing? Donating, and it's going to be donating why? That was kind of a vague question. What I meant is because of these lone pairs. And yet, you guys got it. You answered it in the chat anyway. Perfect. All right, so I will zoom out so you guys can take a picture of these ones. And then I believe someone wanted the chart above. So yes, I will scroll up in one moment. Do, 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 do. So someone said they're confused on one of the examples. Do you mean like in the table or number 9 that we just did? Number 9? Okay, cool. So let's go back to it. So essentially, what we were saying, I'll erase it and we can go through it one more time. So in all the other examples, right, we had this double bond, this triple bond, this diene. It was kind of oriented in a way that made it kind of obvious to you what you're looking at, right? However, this one, I purposely oriented it a different way so that you had to look at both of these groups and figure out which one we're using, right? And it's kind of tricky because at first you kind of don't really notice the nitrogen, and a lot of people will choose to react this group, but then you realize that this is just CN, right? This is a substituent. And we know that CN is going to act as an electron withdrawing group because it's, excuse me, oh my goodness, because it's going to pull these electrons that way through resonance. So we know we're using this double bond to react. So we are going to define it as either a diene or a dienophile. And we know that since it's only one double bond, it's going to be a dienophile. It's not a conjugated diene. And then the last thing we went over is we do have a carbon chain here, right? And this carbon chain is going to be an R group, obviously. And that makes it electron donating. And then someone asked a question, so I'm reading that real quick. Okay, so they said the carbon, blah, excuse me, the CN group and an oxygen when they're part of the double bonds, they're withdrawing groups, which makes it a dienophile. So you're kind of onto something, but not exactly that. So if the oxygen or nitrogen is part of this double or triple bond, that doesn't count as like a diene, for example. So this is conjugated, yes, but this cannot be a diene because this is an oxygen, right? It has to be 4 carbons. And here, it can't be a dienophile, this triple bond, because it has to be 2 carbons. But this triple bonded nitrogen and this double bonded oxygen are both withdrawing groups because the resonance pulls the electrons away, right? So you're also correct with that. The reason, I had one more thing to say about it. Yes, okay. So just because it has a withdrawing group doesn't mean it has to be a dienophile. And just because it has a donating group doesn't mean it has to be a diene. For example, this one we did here had a donating group, but it was still a dienophile, right? So for the most part, they're going to be like diene, donating, dienophile, withdrawing, but sometimes he'll give you something like this just to kind of trick you, you know? I hope that makes sense. I kind of broke up your question into 3 parts and I answered them separately. I hope that makes sense. Let me know if anything doesn't make sense. It does. Okay, you're very welcome. Attendance link. Yes, you guys do my job for me. Thank you so much. I have the memory of a peanut sometimes. If this would love, that would be swagalicious. All my friends hate me for saying swag, ironically, but it has become part of my vocabulary. So, all right, the recording like paused by itself for a second and I was very confused, but it should be back. It looks good. Okay, so we're technically done, but I'm gonna stay until 12:30 because I really want to finish this. If you guys want to go, that's completely fine, but I am gonna finish it. Okay, so which one of these is going to be the most active dienophile? So remember what I said about donating groups make it a better dienophile. Another way of saying that is it's going to be an active dienophile. So essentially, we're looking for the most withdrawing group. What do y'all think the answer would be? You know what? Before I even ask for the answer, let's review some test taking tips. Which one of these is obviously not like the others? A, yes. And so we want most active and we want dienophile, right? A is a what? Yes, someone went, oh, light bulb moment. Yes, so this one is a diene. So if it's a diene, it can't be an active dienophile. Okay, so these 3 are dienophiles. Cool, cool. And now the most active one, is that going to have a donating group or a withdrawing group? Withdrawing, yes. Okay, so this one is a diene because it is 2 double bonds separated by a single bond in the middle. All right, so you guys said most activating is electron withdrawing group. So between B, C, and D, let's look at the substituents. Is this donating or is this withdrawing? Withdrawing, because it has a carbonyl. Cool. Is this donating or is this withdrawing? Donating because of the lone pairs. Coolio, coolio. And then is this donating or is this withdrawing? Our group is donating. Perfect. So electron donating group because our group. Sweet. So the answer is B. Cool. I totally agree. I agree that it's B. Agree, B. Yeah, that rhymes. Cool. All right. I'll give you a moment to screenshot or do whatever you like. All right, so we'll save a couple of these questions for the exam review because I mostly just, actually, let's do these questions now and then we can do the other ones in the next session because I don't want to go like super overtime. Okay, so which of the following molecules would be most reactive? Dienophile. So we're looking for a dienophile, and again, most reactive, so we're looking for electron withdrawing groups. I want you guys to look at it and tell me what you think the answer is, since we did the last one together. One person answered. Tell me why you think it's the answer. Yes, because this electron withdrawing group, that's the only electron withdrawing group present. So this is the answer, absolutely. Yay. Okay, so this next one is asking most reactive diene, right? And so most reactive for the diene is electron donating group. And then someone commented about the OH. So OH has lone pairs. Lone pairs are donating. So that's the difference there. Okay, so for this next one, right, all of these are dying. Cool. And we're comparing now just the substituents. So let's quickly go through. Who can tell me COH? What is that short for? What functional group? It is a carbonyl, but specifically which one? It's one of those shorthands that you guys should know. Aldehyde, yes. So COH equals aldehyde. And CH2OH. What's that? Haha, people said carboxylic acid. That's what I wanted you to think. Nope, that's just an alcohol. A carboxylic acid is CO, oh my goodness, CO2H. So that's how he trips a lot of people up. So please be careful when you see those. All right. So real quick, lightning round. Electron donating group, electron withdrawing group, electron withdrawing group, electron withdrawing group, electron donating group. What do we think of this one?
Electron withdrawing group.
Why do we think so? Like, I don't know. So for this one. So I'm gonna say it's a donating group because we have this carbon, which is lightly donating, and then we have this, which is not necessarily like gonna super donate since it's kind of far away, but it has those lone pairs. So I'm gonna say this is a very weak electron donating group. And then for the last one, we have two alcohols, which are two donating groups because they both have lone pairs. And then someone had unmuted. Did you have a question?
Yeah, does that picture you drew of the carboxylic acid correspond to number 4?
No. That's a great question. I was just comparing CH2OH versus CO2H. So this is just kind of its own separate thing. I'll move it over here and put it in a little box. Okay, and then someone asked, will I be posting the video for tutorings or not? So I don't record all of the tutoring sessions just because one, I forget, and two, sometimes we don't really go over too much. There was one session this week that I will be posting, but that's pretty much it. So all the sessions that I have recorded have been posted or will be posted today, basically. Okay, so I think we're gonna finish off here for now. I don't want to keep you guys too long. We'll go over anything else that's left over during the next session. Oh, duh, I didn't give you an answer. Wow. Um, I'm so sorry, guys. I'm so tired today. So yes, the answer would be 4 because it has the strongest electron donating groups because lone pairs donate more than R groups. Excuse me, I have the hiccups. Now that I've given you the answers, I will free you guys for the day. I will stop the recording.